Okay, like Sudhir, so Arnav is also alumnus of this in this institute. He did 2 years MSc and graduated in 2007. Then he went to US for about 8 years. He did a PhD for 5 years in Arizona State University, then a postdoc in Pacific Northwest National Laboratory. And in 2015, he came and joined IIT Gandhinagar as assistant professor. And in 2020, we asked him to come back to IIT Bombay as a faculty. So in 2020, he joined and currently is a associate professor. He's a Ramanujan Fellow and is also associate of Indian Academy of Sciences. He's our he's also associated with the interdisciplinary program in climate studies. He's one of our rising star in the department and there's a long way to go.
Okay, so thank you. So after we solve this particular challenge, now we look for global challenge. At this moment, one of the global challenges we have is the climate change. And before we go further, first I'd like to thank Professor Ravi for this nice introduction, and thanks to IRCC team for this opportunity to display our research to all this audience. So we all know that at this moment we are facing a huge problem with respect to carbon dioxide. It is coming everywhere and it is accumulating in our atmosphere, creating a lot of climate change issues. Even our world leaders agree that it is a problem, we need to find a solution. Now, what is the solution? One of that approach was that can we actually use the renewable energies and use it for our systems? Quite good, but is it sustainable? Not always, because the renewable energies are not really strong enough to provide a power pack energy resource like the petroleum, coal, or oil. So that is why we cannot use it directly, and at the same time, they're not always reliable. Sometimes they're coming, for example, a sunny day like this is good, but remember those days of monsoon, we don't have enough sunlight to charge up our solar panels. So there is a system that we need to use these renewables in the form of chemicals, and over there we need a solution how we can convert these renewable energy resources to chemicals. And one of those things we are actually learning from the nature, which is happening for millions and almost billions of years, is the photosynthesis. Using solar energy converted to chemicals where we are actually capturing carbon dioxide and converting it to carbohydrate. Can we do the same thing and produce hydrogen? So why hydrogen? A small molecule, relatively easier reaction than a 6-step reduction of the carbon dioxide to carbohydrate. But over here, the problem is how we can make hydrogen at a very sustainable way. And for that, we need catalyst. And over there, our research group is focused on producing catalyst for hydrogen production. Now, hydrogen will produce from proton. What is the major resource of proton that is available all around the world? Water. So from water, we want to produce hydrogen. That is our goal. And why hydrogen? Not only for energy transaction, we are already using hydrogen in a lot of amount. It's a huge market already available, and that is our government, Adani's, Ambani's, everybody is looking for hydrogen. So now, hydrogen is again not something new in the form of biology. They are actually using hydrogen for a long time. And they are using this enzyme called hydrogenase, which I am showing you over there. And this actually consists of some ions and a huge protein cluster, which actually plays their magic. They all come together and synchronously exchanges protons and electrons so that the hydrogen can be made. Our goal, can we replicate this enzyme and make a synthetic analog of it? For that, we took this cobalt complex. Cobalt is an abundant metal, always available, and it has a particular set of ions which is binding to that, which is called the ligand. And over there, you can see a group is actually hanging over there. Over here, we tried to apply that this whole protein structure actually plays a huge role when this enzyme is working nicely. Can we replicate that factor over here? We are not going to produce a system with the protein, but the most essential and important factor of that, amino acids. And over here, we are going to tether an amino acid, and our goal is, can these hanging amino acids, far from where the cobalt is, can affect its reactivity? So we make particular complexes with 2 natural amino acids and 2 of their analogs and 1 control complex, and then we put them in water, and then we actually put electricity over there. Our goal, this complex present in water in soluble form, when you put electricity, can it produce hydrogen from that water? For that, we did an experiment called electrochemistry. Basically, it says that if the electricity is producing hydrogen, we are going to see some exchange of electrons, which we can actually measure in the form of current. So this scale, Y scale, is actually current. If you see an increase in the current, it shows, yes, we are actually exchanging electrons and producing hydrogen. Hydrogen, we actually provided the proof from an analytical method. But over here, we show, yes, it is working. And over here, when we are actually adding these amino acids, it is improving the rate of the same system without the amino acids by almost 10 times. So that means we can actually replicate the enzyme structure even in the form of a single amino acid. So that is all good, but it is maybe our fantasy. We are thinking that this amino acid is helping me to exchange proton. What is the proof for that? For that, we did an experiment called NMR spectroscopy. We have a lot of them in our campus in chemistry department. And over there, they actually give us a glimpse what is actually happening around the molecule. And over there, we see a lot of these protons are actually exchanging between them. And over there, the water molecules are also participating for this relay of protons. So which is known as the proton relay, and we are able to replicate that. We're also able to find some crystal structures where we see that water molecules are very nicely poised around this system and connecting the far-fetched protonic group to the actual active site. So that's very good. So we published papers, we are very happy, but the thing is that, are we going to stop with only one single amino acid? Can we go further? So for there, we found that when we are making these complexes with amino acids, we have to do a synthetic step where we are adding our natural amino acids to this particular ligand. Our goal, can we actually go to some other functional groups which is found in biology where we don't even have to do the synthesis. We can directly take that molecule from biology and include that in our catalyst. For that, we found vitamin B6 is one of the important one. It is obviously important from our system, but as a chemist, we look into it and found there are two of them which can bind to my same cobalt complex very easily and have some groups which can help me to exchange the proton. So we did the synthesis, we do the studies, and we found, yes, we can actually make a catalyst even with the vitamin. So vitamin can not only help the human beings to make our health better, also makes the health of a catalyst also better. And this is actually a system which works in presence of water, in presence of air. So you can say it is an all-weather ready catalyst. Then we actually opened up the Pandora's box. Why to stop only with the vitamin? We can make catalyst with drug molecules. We can make catalyst with neurotransmitters and even nucleotides, which is a part of our DNA. So over here, we are expanding the pool, what the biological molecules can do, and make some catalyst out of it to find even a newer role for those catalysts. So you can say it is evolving our system. So far, whatever we are actually doing, we are doing in a small scale, and over there, in a small boxes like that, small RBs like that, where we are actually working them, producing some few bubbles of hydrogen. Pretty good proof of concept. But what we need, million tons of hydrogen. That means billion liters of hydrogen. So we need some system which can work at this particular scale. So these are human beings, so you can see the size that we are actually need to go. Our catalysts are not ready there yet, but how we can prove forward. So over there, our thought process was, can we make this catalyst from the water to a solid surface, a heterogeneous system? Then we can put them as we put our filters, and over there, we can actually catalyze the system. Over here, we take silica, basically is a sand. We actually do some chemical modification of that, and then we put our catalyst on top of that. So this is, we start from the original silica, white color powder, and end up with the catalyst grafted on that with this brown powder. So now we can say we actually have catalyst on a solid surface. From there, we actually looked into it. We found that it is doing hydrogen production, so it is retaining its reactivity. At the same time, it is doing also oxygen evolution. So over here, why it is important? When we are talking about green hydrogen, basically we are doing electrolysis of water. Obviously, we are going to produce hydrogen, but over there, there's another half cell of that reaction, oxygen. So oxygen and hydrogen both needs to be produced. And over here, if we only consider the catalyst needed for the hydrogen, what is going to happen for the oxygen side? So we need two sets of catalysts. And serendipity, you can see that this catalyst is doing both sides of the reaction. So I can take the same catalyst, put it on two electroactive surfaces, and assemble that in the same solution. One side will produce hydrogen, one side will produce the oxygen. That we do. Still, some bubbles of hydrogen, how we can move forward. For that, we need an electrolyzer. Over there, we need to pack them down. So for that, actually, I send my student to the market, buy a commercial one. We'll remove what is actually available commercially. Right now, we use platinum, much expensive. We'll wash out the platinum. We'll put our own catalyst, which is made out of cheap cobalt, and then run the full system. But unfortunately, the commercial ones are too expensive. Even with the very good support from the IRCC, we cannot afford that. So we said, like, we are at IIT Bombay, we can make our own system. So thank you to the students. They actually made each and every component of an electrolyzer, all designed at IIT Bombay. And over there, we made the first one, which is made out of this. This is an aluminum one. This is a very nice electrolyzer. And then we actually made it out of a acrylic one, so that we can even see what is actually happening inside. And from there, we actually put the first set of the electrolyzer, which is actually have one set of electrode from the cathode. This is producing hydrogen, one set producing the oxygen. Put together, we call them the one stack. Produces a few liters of hydrogen in a day. But for the practical level, we need a system like that where we can put all those stacks together. And over here, today, we actually also bring it up. So this is the stack we designed in IIT Bombay, which actually produces 20 liters of hydrogen in a day. It fills a lot, 20 liters of hydrogen, but hydrogen is a very light gas, so it is not enough what we need. We need multiple of them, but we are actually on the way to go forward to that. So today, I tell you the story. Oops. So today, I tell you the story that over here, we are able to start from a very basic cobalt system, understand how the architecture of a biology works, then go take the help of the biology, evolve that further, and now we have come up to here. We can still say it is the early stage of the electrolyzer, same as my career so far, but our goal is to reach into a system where we can be sustainable and we can produce hydrogen what we need at the global level. Thank you. Thank you very much.